All right, here we are in the Laurel Forum again in Carpin Hall, room 139, back on campus for a couple more sections. We're going to talk about section 9.3 today, continuing with our combinatorics. We just finished talking about multiplication rule and possibility trees, which gave us a means of counting the number of possibilities and sometimes the probability of various events that involve outcomes taken in multiple steps. So if one step of the process yields n1 possibilities and the next step of the process yields n2 and so forth, then the number of possibilities of this multi-step process is found by taking the product of the various single-stage probabilities, n1 times n2 times n3 and so forth. And a possibility tree, if you recall, from section 9.2, gave us a pictorial means, a graphical means of understanding kind of keeping track of all the different possibilities that could arise, because each horizontal stage of the tree as it grew outward to the right captured all of the possibilities after coming out of a single point at a particular stage. So we're going to move to counting, a different kind of counting now, rather than looking at multi-stage processes that enable us to find, or in which we're asked to find the total number of possibilities. We're going to look at processes, not so much processes, events that take place at a single point in time, but that involve maybe multiple choices, multiple selections, some events that overlap with one another. So we're going to learn about the addition rule, the difference rule, which is related, as you might suspect, to the addition rule, the complement, and inclusion-exclusion. And again, all of these are rules for counting objects or counting events that might have some sort of overlap, but all occur at one point in time. So let's go ahead and talk about the addition rule. Now, a lot of these events from section 9.3 are best illustrated graphically using Venn diagrams. And we've used Venn diagrams already to talk about sets and to understand the interaction of various logical ideas. Like if we had one set contained inside of another, then being a member of the inside set implies being a member of the outside set, and so forth. So we've seen Venn diagrams already. They come up again in the addition rule. I'll write the rule down and then I'll picture it graphically. Oops, not the addition, the addition rule, which says that if you have a bunch of disjoint events or outcomes from some process, if A1, A2, and so forth up to AK are all disjoint events. And what this means is they can't occur together. They all are distinct from one another. So if I roll a die, for instance, rolling a 1 is distinct from rolling a 2, which is distinct from rolling a 3. Or rolling an even number is disjoint from rolling an odd number. Those events don't occur simultaneously with one another. So they are disjoint from each other. Then if A is the disjoint union of all of those events. And what I mean by that, this is the collection of all possible outcomes that are found from taking one or another of these events. So an event, an outcome is in A if it's in one or more of the sets AI, or one or more of the events AI. Now, because these are all disjoint events, when I say one or more, it means it's going to be in exactly one of them. So this is sometimes called the disjoint union. We'll talk about unions a little more generally in a little while, but the disjoint union is what you get if you take all of these events and you lump them together, and we just say disjoint to remind ourselves that there's no overlap between these individual events. So in pictures, what this would look like is if I had a set A, it might be that I've broken A up into a bunch of disjoint subsets, AI, each of which corresponds to one of these events. So this is the picture you want to have in mind when you're thinking about disjoint union. So if A turns out to be the disjoint union, then the number of outcomes in A, remember this is the notation we use for the number of outcomes, stemming from section 9.1 and 9.2. Well, how do you count the total number of outcomes in A? If you think about A in this fashion, this disjoint collection of little subsets AI, it's pretty clear that the number of elements, the number of outcomes in that set, is just going to be equal to the sum of all of the sizes of the AIs. So to get the total size, the total number of outcomes in event A, you just add up the size, the number of outcomes in all of the sub-events, the little events AI that go into A. This is it. This is the addition rule. And we use this subconsciously when we're counting things quite often. If I give you 2 boxes of things and I ask you how many things are in one or another box, all I'm asking you to do is to count the objects in one box and count the objects in the other box and add them together. So this is one of the most basic rules in counting. And it's also useful when you have subsets. So another rule, as I mentioned this at the outset, another rule for counting that we also use just subconsciously, we don't even think about it because it's so intuitive, is the following. If we have one event contained inside of another, and we want to know, obviously, since B is contained inside of A, it has fewer elements, has fewer outcomes than A does. If we want to know something about the difference, what I'm writing here is the set difference. And just as a reminder, this is the collection of elements that are in A such that X is not in B. So if I want to count the number of elements, the number of outcomes that are in A but not B, that's what I'm getting when I take this difference. Notice that's why we needed B to be inside of A, because you can't take away things that aren't in A. Well, all we would do is compute the number of objects that are in A to begin with and take away the number of objects that are in B. And again, this only works because B is contained inside of A. Otherwise, we'd be taking away conceivably more things than were originally contained in A. So between the addition rule and the difference rule, we have some pretty basic counting principles. And it gets a little more, we can talk a little bit more broadly. We can talk a little bit more broadly, a little bit more generally. Get my whiteboard position correctly. There we go. All right. We can talk about taking complements. So we have what we could call the complement rule. So remember, all of our action, when we're talking about probability and combinatorics, generally speaking, all of our action is taking place inside of some universe of possibilities called a sample space. So if A is an event in the sample space S, again, this is all possible events that we could have, all possible outcomes of some experiment or process. If A is an event in sample space S, then the complement of A, which your textbook denotes, there are several standard notations for this, but your textbook denotes it by A superscript C, which you get in LaTeX just by doing a caret symbol, like the exponent symbol, C, just like you would expect. The complement of A to the C, A complement, is defined by the following formula. You take all of the possible events that there are in your universe of possibilities, your sample space, and you take away A. So it's just the set difference between the sample space and the event A. And obviously from the difference rule, the number of possibilities in the complement is equal to the number of total possible outcomes minus the number of outcomes in the event A. Now, if you remember back in section 9.1, to find the probability of an event, all we did, to find the probability of an event, all we did was we took the number of outcomes in that event and we divided by the total number of outcomes in the sample space. So the probability, for instance, of the complement would be the number of elements in the complement divided by the number of elements in our sample space, because that was just how we computed the probability of an event. Take the number of outcomes in the event and you divide by the total number of outcomes. But our formula we just determined from the complement rule, which told us how to count the number of elements in the complement. Again, this is the stuff going on outside of A. Everything in S outside of A would be your A complement. We have this formula, so we can replace our numerator with that formula. Oops. And now we can break up into two different, since we have a difference in the numerator, we can break that up into two different fractions. And notice the first fraction we get, n of S, the number of elements in the sample space, divided by itself, is just 1. This is just 1 minus this value. But this is just the definition. When you take the number of elements in an event and you divide by the total number of possible outcomes, total number of possible elements, that's just the probability of A. So what we've done is we've determined not just a means of counting the outcomes in the complement, but also determining the probability of the complement. And this kind of makes sense here if you think about it. The probability of the complement of an event is 1 minus the probability of the event itself. Meaning, if you want to find the probability of something not happening, all you do is you take 1 and you subtract the probability of the event happening. That makes sense because we think of probabilities in terms of percentages, and percentages in terms of decimals. So a probability is always a number between 0 and 1, like a percentage likelihood. So the percentage likelihood of something not happening is equal to 1 minus the likelihood of it happening. Put another way, if you add up, we added this to the other side and we had 1 equals probability of the complement plus the probability of the event itself. The probability of the event itself and its complement happening sums up to 1. It either happens or it doesn't with 100% certainty. So there are a couple of different ways of looking at this formula that make intuitive sense. I'd love for you to understand not just how we derived this, but also what it means intuitively and why it makes sense intuitively and shouldn't be too surprising. So make sure you pause the video if you haven't already to think about the intuition behind this, both the pictorial intuition and the derivation we did and what we came up with at the end, sort of the interpretation of this. And again, make sure if you aren't fully understanding this, go back to the other side of the board, rewind the video, go back to the other side, and take a look at the addition rule and make sure you're understanding the disjoint union. We're going to talk about one more principle, then we'll do a few examples and wrap it up for this video. The last thing I want to talk about sort of takes all of what we've done so far and puts it in a slightly more complex context, and that is in inclusion-exclusion. So the inclusion-exclusion principle or rule deals with throwing things in and then taking them out to count a slightly more complicated set. So if A and B are, actually that looks like a B, not necessarily disjoint events. So here's what the picture is going to look like. We're going to have A, we're going to have B, and we're going to have some overlap. That is, of course, what we call the intersection. A intersect B. By the way, in LaTeX, you would do this with A \cap B. And then you want to end math load \CAP. That's what you get to get the little upside down symbol to denote the intersection. This entire set is, of course, the union, A union B. And the way you would do that in LaTeX is A \cup. C-U-P, B. Please don't use the letter U to denote union in LaTeX because it looks really ugly and I will probably be tempted to take off points. I probably won't actually take off points, but I'll be tempted to do that if you use a U because it just looks sloppy. That's the whole point of doing LaTeX is to get it to look not sloppy. So please don't use U. Use \CUP. Good? All right. So here's the idea of inclusion exclusion. Suppose that we want to count the number of objects or the number of outcomes in this set, this entire set. I want to make sure I distinguish this from the previous computations. How would I do that? I just realized I walked off camera. So it's like a ghost is telling you how to do the inclusion-exclusion principle. I see dead formulas. All right, how would we count the number of outcomes in the union of the sets A, B? Well, it's really tempting to just say, like we did before with the addition principle, let's just take n of A and n of B, right? We'll throw them all together. We'll throw all of these objects in, and then we'll throw all of these objects in. The problem is, if you notice what I just did, slow-mo, and then throw all of these objects in. You'll notice that there were a bunch of objects I put in twice, namely, any of them lying in the intersection. So I'm overcounting things in the intersection. And I have to take that away. But it's that easy. We include some stuff, and then we exclude some stuff. And that's why this is called the inclusion-exclusion principle, because we're throwing some stuff in, and then we're taking away the overlap, because we overcounted it. So this is an example where these rules that we've used already, the addition rule, subtraction rule, not so much the complements, that's a little separate, but the inclusion-exclusion principle draws on the addition and the subtraction rule. So go ahead and pause the video, if you haven't done so already, and take a moment, make sure you understand all these ideas. We'll do a couple examples before wrapping it up. And I'll give you a little quiz. That's what I do. By the way, it is a gorgeous day outside on campus today. I've seen precisely one other person on campus the whole time I've been here. There's a retired faculty member from the English department who, even during normal circumstances, is here more often than any of the folks who actually still work in the department. Like literally, he's here from like 8 in the morning till 5 p.m. pretty much every day. I hear rumors that he doesn't have internet at home, so he comes to campus to use the internet here, which, you know, I guess that's a reason. All right, he's the only other person I've seen today, by the way. I meant to say that. Okay. So how many integers are there between 0 and 100? Here's an example. How many integers are there? So count the integers from 0 to 100 with the digit 7 appearing at least once in them. How many integers are there between 0 and 100 that have at least one 7? Now, if you think about it for a second, you realize that most of the integers from 0 to 100 have either 1 or 2 digits, and you can group them kind of by tens. There's going to be the first 10, the next 10, and so forth. And in each group of 10, you're going to have integers that have a 7 in the ones place. So they're going to be ones place. I put the quotes in the wrong place. Ones place integers, which have a 7 in the ones place. So you get 7 itself, 17, 27, 37, and so forth up to 97. And if you count, this is going to give rise to, if we call this set, the set O for ones place integers, we get 10. The number of elements, the number of outcomes in the event O is 10, right? Because there are 10 such. We also have, I'll call this the set T, I'll call this the tens place integers with 7 in them. Now these are the integers where 7 appears in the tens place. And we've got 70, 71, 72, up to 79. Right? And then we go to 80, so we're out of that set. And you can see here too that the number of elements in the tens place integers is also 10, because we have any number of any one of 10 possibilities for the ones place, 0 through 9. Just like we had any of 0 through 9 as the possibility for the tens place in the ones place integers. So the number of integers with a 7 is just going to be the number of integers in ones place. Right? It's the number, it's out. It's not. The number of integers in the ones place or the union with the tens place from our formula is the number in the ones place plus the number in the tens place. They're not disjoint. If they were disjoint, it would just be the addition rule. But they're not disjoint. There's something in the intersection. And I was kind of sneaky because I stopped before we encountered it. There's one number in both of them. 77 will occur in both of them. That's the intersection of these sets. So we have to take that away. Oops. All right. So the inclusion-exclusion principle is necessary here because we do have one element in the intersection. Does that make sense? The size of the union is the sum of the sizes of the two disparate sets, they're not disjoint, minus their intersections. We get 20 minus 1, or 19. Now, if you were just kind of casually counting the integers, you'd probably arrive at the same formula. You just would do it subconsciously. And here we can see how the formal principle that we just had on this board a moment ago before I erased it, the inclusion-exclusion principle, actually gave us that formula doing it carefully. All right, so here's another example. Suppose we survey our class. We survey our class. And there happen to be, by the way, there are 21 of us in class. Of 21 folks, actually, I'll throw myself in there, 22, because why not? Let's say 20 have Facebook. We're old school. 12 are really old school and have MySpace. I mean, I saw the band page. I don't really, but pretend. And only one MySpace user does not have Facebook. So this is some information. And I claim that this is going to be enough information to tell how many of us are on at least one social media platform. Okay, so the question is, how many? Let's see. Is this actually going to work? I'm going to make sure this is going to work. I was remaking the numbers in my head because I had old numbers corresponding to a different size of class. I have no idea why this is helping, but it seems to. So 20 have Facebook, 12 have MySpace, only one has... Yes, this will work. All right. So here's how we can handle this. Let's do a Venn diagram. So we have 20 folks, this is our Facebook over here, and the total number of people in Facebook is 20. So all these people have Facebook. There are 20 of them. And over here we have MySpace. We have 12 of them. And there's some overlap. So the total number here is 20. The total number here is 12. But we also know there's only one person, one lonely holdout from the 1990s. Well, maybe not the 90s, but the early 2000s, early 2000s. There's one holdout, person that has MySpace but not Facebook. All right? So what does that mean? That means that tells us something about how many people are in this intersection, right? This, since this total number is 12 over at all of MySpace, and there's only one person right there that is off on their own, that means that in this intersection, there are going to be 11 people, because it's all of the people in MySpace except for that one, and we knew there were 12 people total. So the intersection is going to be found, and if you want to, you can do this formally. The size of the intersection of Facebook and MySpace is going to be, we're going to turn the inclusion-exclusion formula on its head. We're going to take the size of Facebook and the size of MySpace, and we're going to subtract the union of the two. So that determines the intersection. But what we really wanted to do is we wanted to count how many people were on one social media platform or the other. That would be determined now by taking the original inclusion-exclusion. So if we want to find how many people are on F-bombs, Facebook, Union, MySpace, we take the number of people in Facebook, the number of people in MySpace, and we subtract the number of people we now know are in the intersection. And again, we got that just by arguing, well, there's one person outside the intersection in MySpace, which meant there must have been 11 in it. So how do we do this now? We have 20 people in Facebook. So what I'm doing now is I'm just plugging in this number. 20 people in Facebook. We have 12 people in MySpace. And we have 11 people in the intersection. So it turns out that there are 21 people. 20 plus 12 minus 11 is just 1. So we get 21 people on one social media platform or another. So that's almost everyone. Just the way I made up the numbers, almost everyone in our class would end up having social media if these were the numbers. So again, all we're doing here is a little bit of logic to figure out how big the intersection must have been, because only one person with MySpace was not in the intersection. And once we had that information, it was a simple matter of computing using inclusion-exclusion to figure out how many people were in one set or the other. So let's wrap up with one more example, and we'll call it a day. I'll give you a quiz at the end of that. So I want to make sure I'm doing okay on time. I've got to wrap up pretty soon because I think I've got a Google Hangout to get to in about 9 minutes. I'll come back in a little while and we'll record a video for section 9.4 to put under next week's Moodle topic. So this next one is going to have to do with passwords. As you all know, passwords are developing increasing sophistication and complexity in terms of what you have to include in it. We're going to suppose that UNCA adopts a new password protocol. So UNCA passwords, example. UNCA passwords must, let's say, be 5 to 7 characters in length, contain at least 4 letters. We're just going to assume from A to Z, the English alphabet. Contain at least 1 digit, and all letters must come before all digits. This example is going to make use of both the addition and the multiplication rules. And we'll see why in a moment. There's a little bit of counting involved here. So we want 5 to 7 characters, and you can see that that is long enough. 5 characters is long enough to have at least 4 letters and at least 1 digit. But there's a little flexibility because of the 7 characters in length. What I'm going to do is enumerate all possibilities in terms of the shapes of the characters and the digits. And then we'll use the multiplication rule to figure out the number of possibilities in each of those categories. Having done that, these are all going to be disjoint categories, so we can add them together using the addition rule. All right. So our first possibility is we've got 5 characters. We've got 5 character passwords. We've got 6 character passwords. And we've got 7 character passwords. Those are the different lengths we could have. Inside of the 5 character passwords, we know we need at least 4 letters and at least 1 digit. Well, that's the only possibility, because as soon as you have 4 letters, you're forced to have only a single digit at the end. If you have 6 characters, however, you could have 4 letters followed by 2 digits, or you can have 5 letters followed by 1 digit. Under the 7 character combination, you could have 4 letters followed by 3 digits, or you could have 5 letters followed by 2, or 6 letters followed by 1. So this is kind of a standard practice in combinatorics, is to figure out sort of the highest level organizational structure you can to enumerate all possibilities, sort of enumerate all possible categories, and then within the categories, let's see if we can count. Remember the multiplication rule. We're choosing 4 letters and 1 digit, so the number of ways to choose each letter is 26. So choose your first letter, 1 of 26 ways, times 1 of 26 ways to choose your second letter, times the third letter 26 ways, times the fourth letter 26 ways, and then 10 ways of choosing that last digit. Similarly, for 4 letters, 2 digits, there are 26 to the 4th times 10 squared, or 100 ways. There are 26 to the 5th times 10 ways of choosing 5 letters followed by 1 digit. You can do 26 to the 4th times 10 cubed ways for this particular configuration of password. 26 to the 5th times 10 squared, followed by 26 to the 6th times 10. So now we've enumerated all the different categories of passwords. To find the total number of passwords, we've used the multiplication rule so far. Now we use the addition rule because none of these are overlapping. These are all disjoint possibilities. So the addition rule says we can just add up the number of ways of doing each of them. And I'm not even going to bother because math is hard. These numbers are big. I'm not going to bother to multiply this out and figure out what the number is going to be. But whatever this sum turns out to be, adding up all those possibilities, that is the number of passwords that UNCA would allow. All right. So here is the quiz for a section. I believe we're on CE7. I believe this is CE7. This is a little easier than the last example we just did here. And this quiz will be due on April 17th, I believe. These sections are all for April 17th. This is for April 17th. So CE6. This is the quiz. I said 7, I think, right? I think this is CE7, COVID era 7 quiz. Go ahead and answer this question. In a class of 20 students, 12 are vegetarians. Pretty typical sample from UNCA. And 10 are gluten-free. if 5 students have neither restriction, how many have both? How many have both? And as usual, I'll put up a link to this quiz in Moodle so that you can do it, just answer it inline in Moodle. I hope that's working out well for everyone. So again, this is going to be an inclusion and exclusion puzzle. Yes. Go ahead and do this one. Get it in by, again, I believe the due date for this quiz will be April 17th, because this is the last section in the current week, which means its problems are due in the following week. It's been a pleasure. And I'll be back at you in a little while with section 9.4. Thank you so much. And as usual, email me if you have any questions.